Consider a beam of electrons of mass m approaching a potential barrier as shown here. Here L is the width of the potential barrier and V0 is the height of the potential barrier. Classically, if the electron is having energy greater than the barrier height, it will be transmitted to the region 3. However, if the energy of the electron is less than V0, it will always be reflected back at the barrier. So region 2 is a classically forbidden region and there is 0% chance to find the electron in this region if its energy is less than the barrier height. However, quantum mechanics predicts a different picture. Even in such cases, the electron wave function is not sharply going to zero at the boundary of the barrier. Instead, it extends into the forbidden region where it exponentially decreases as we move away from the boundary and finally reappears on the other side of the boundary where it again has an oscillatory behavior as in region 1. This passage of electron from one allowed zone through a classically forbidden region into another allowed zone is defined as the tunneling process. The tunneling probability or the transmission probability is given as a e raised to minus 2 alpha L, where a is a function that depends the energy of the electron and the barrier height, and alpha is defined by this expression. You can see that the amplitude of the transmitted wave is much smaller than the amplitude of the incident wave. How small it depends the width and height of the barrier. If the barrier is very high and or too broad, the value of alpha becomes large. If the barrier has infinite height, then we would expect no electron to be transmitted to the region 3 through region 2. Otherwise, there will always be a finite probability for electron to tunnel through the forbidden region, and that is given by this expression. For photons also, the classical physics predicts a complete confinement of photons in the region of confinement. That means the photons get 100% reflection at the boundary of confinement and there is no chance to leak out. Here also the quantum theory predicts a different picture. The field distribution of light confined in a waveguide can extend beyond the boundaries of the waveguide. Light can leak into the regions outside the waveguide, which is a classically forbidden region. So that is shown here. You can see that the electric field distribution is not completely confined within this high refractive index region. It has some tailing into the region where we do not actually expect any electric field as per classical physics. This leakage of light generates an electric field called the evanescent wave. This passage of photons through a barrier layer of lower refractive index is called photon tunneling. The field distribution in the region outside the waveguide, which is the classically forbidden region, it does not behave like a plane wave. Instead, the electric field amplitude extending into the classically forbidden region decays exponentially with distance x into the medium of lower refractive index from the boundary of the region according to this relation E equal to E0 e raised to minus x by dp, where E0 in this equation is the electric field at the boundary of the waveguide and dp is called the penetration depth and is defined as the distance at which the electric field amplitude reduces to 1 by E of the amplitude E0. Typically the penetration depth dp for visible light are 50 to 100 nanometer. This evanescent wave can be used for nanophotonics as the optical interactions manifested by the evanescent waves are localized within a few nanometer range. So this is one way of confining light, and keep in mind that it's not the propagating light. The propagating light is actually in the region where it is confined, but this is a leaked portion of the electric field or light, and that is spatially confined into a nanometer length scale. So that part can be effectively used for nanophotonics applications. Now we are going to analyze the motion of electrons in a crystalline solid and how the motion of electrons gets modified by the atoms. To keep things simple, we will assume that there is no direct interaction between electrons. Since we are considering crystalline solid, the atoms are arranged in a periodic pattern, and hence the crystal introduces a periodic potential energy for the electrons. If we initially consider the motion of electrons along x direction only, then this figure gives the sketch of potential energy seen by an electron along a line of nuclei. Each of these dots represents a positively charged atom or ion through which electrons move. Whenever the electron is right on top of the nucleus, its potential energy drops to the lowest value. Close enough to the nucleus, a very strong attractive Coulomb potential is seen. In the middle of the two nuclei, the potential energy will be zero as the electron is under equal potential from two neighboring nuclei. Crony and Penny developed a very simple one-dimensional model that explains the motion of electrons through crystal. In this model, the potential felt by the electrons are assumed to be a square well type, where electrons at each atomic locations is assumed to be inside a potential well of height V, such that the electron energy E is less than the barrier height. So the potential energy seen by the electrons is periodic with a period A, which is the lattice constant along x direction. If we solve Schrodinger equation for this periodic potential, we get some interesting result. If you plot the energy as a function of momentum, you can see that energy of the electrons are not continuous. There happens sharp discontinuities in the energy spectrum for some specific value of k. There occurs some gap in the energy spectrum at these points, and they are known as the energy gap or the band gap. These are the ranges of energies for which there is no solution for Schrodinger equation exists. Remember that the region bounded by the values of k from minus pi by a to plus pi by a is the first Brillouin zone, and between minus pi by a to 2 pi by a on either sides are second Brillouin zone, etc. Recall that while discussing Brillouin zones in the previous semester, I had mentioned that Brillouin zones are the allowed energy regions in momentum space for electrons present in a periodic crystal. Now this point must be clear to you. Very interesting things are physically happening at these points. The electrons present in the periodic crystals are commonly referred as Bloch electrons or Bloch waves. At the boundaries of Brillouin zone, the group velocity of the Bloch waves tends to zero, and consequently the standing waves are formed at the boundaries. In contrast, within the Brillouin zone, Bloch waves behaves as traveling waves. Such a change in the behavior of Bloch waves from traveling to standing wave formation results in the origin of energy gaps at the boundaries. This is commonly called Bragg diffraction of Bloch electrons at the zone boundaries, and it depends on the crystal structure under investigation. The magnitude of band gap and shapes of energy bands are ultimately determined by the nature of periodic potentials involved. The message I want to convey you is that the motion of electrons in periodic lattice is characterized by the bands of allowed energy separated by forbidden regions. Also note that the width of allowed and forbidden bands increases for higher values of electron energy. In principle, it is possible to have an infinite number of such energy bands. However, since the number of electrons in a crystal is fixed, only first few energy bands will be occupied by the electrons. The highest occupied energy band is referred as the valence band. For example, suppose we have a crystal in which first three bands are occupied by the electron, then this band is called the valence band. The first unoccupied band is called the conduction band. The energy separation between the valence band and conduction band is called the band gap of the material. When we discuss the band structure of crystals, we usually consider the valence band and conduction band only, as the electrons in the bands below the valence band are usually do not influence the properties of the crystal. Those electrons are called the core electrons. Now, based on the way the conduction band and valence band is separated, crystals can be classified into conductors, semiconductors, and insulators. The difference between these three categories of materials are clearly evident here. You can see that in the case of conductors, there is no energy gap between the valence band and the conduction band, and hence electrons can easily take part in the conduction process by applying a small external electric field. In the case of insulators, there is a large energy gap between the conduction band and the valence band. Usually the valence band will be completely filled and the conduction band will be completely empty. Such materials do not conduct electricity as there are no free electrons to take part in the conduction process. Semiconductors are a class of materials in which there exists an energy gap as in the case of insulators, but this band gap is very small compared to the band gap of the insulators, and hence some of the electrons in otherwise fully occupied valence band can make transitions to the conduction band and then take part in the conduction process. For this, the electrons need some additional energy which they usually get from thermal agitations in the crystal. Hence, you can see that they are just like perfect insulators at 0 Kelvin and has some conductivity as temperature increases. This particular representation that we discussed is known as extended zone scheme. Sometimes it is helpful to repeat the first Brillouin zone periodically through the whole K space, and this representation is known as reduced zone representation, where I have translated the bands in other zones to the first zone by translating it to an integer times 2 pi by a, where 2 pi by a is the size of the first Brillouin zone. So this is a consequence of symmetry or the periodicity of the crystal, which allow us to look into the first Brillouin zone alone to understand the contributions of all Brillouin zones. The bands can take very simple structures or simple shapes like this one instead of considering this kind of a complex representation. Now, the band gap energy is often labeled as Eg, and it plays an important role in determining the electrical and optical properties of the semiconductors. The dispersion relation for each band has a parabolic form, just as for free electrons. The energy of an electron near the bottom of the conduction band is given by E0c plus h cross square k square by 2me, where E0c is the energy bottom of the conduction band. Similarly, the energy of an electron near the top of the valence band is given by EV0 plus h cross square k square by 2mh star, where EV0 is the energy at the top of the valence band. Me star and Mh star represents the effective mass of electrons and holes respectively in the crystal, which can be obtained from the curvature of the band structure. Crystals are classified into direct bandgap or indirect bandgap materials depending the way the conduction band minimum and the valence band maximum is appearing. In direct bandgap materials, top of the valence band and the bottom of the conduction band are at the same K value. The best example is the gallium arsenide, which is a well-known material which usually show very strong optical absorption or optical emission, since the momentum is always conserved in the transitions between the conduction and valence band. Whereas in the case of indirect bandgap materials, the top of the valence band and the bottom of the conduction band are not at the same values of K. And silicon is a well-known example for indirect bandgap semiconductor, and such materials usually have very weak optical absorptions and emission is prohibited because of the momentum mismatch. Keep in mind that what we are talking is the case of electron waves within crystal, not something sent from outside. We have seen that the band gap originates at zone boundaries because of Bragg diffraction of Bloch waves. The condition for this to happen is given by the Bragg's law, m lambda equal to 2d sin theta, where lambda is the de Broglie wavelength of electron, d is the lattice spacing, m is the order of diffraction, and theta is the angle between the electron wave and the Bragg plane. If you assume first order diffraction with electron waves propagating normal to the Bragg plane, then we get the relation lambda equal to 2d. This gives us an important information that for Bragg diffraction to happen, the de Broglie wavelength of electron must be of the order of lattice spacing. It also suggests that not only the electron waves in the crystal, any subatomic particle waves or electromagnetic waves with wavelength comparable to the atomic spacing can produce diffraction effect. This is the case of X-ray diffraction in crystals, where X-rays have wavelength of the order of a few angstrom, which is comparable to the sub-nanometer interplanar spacing in most of the semiconductor crystals. It must be clear to you that periodic potentials can produce diffraction effects which leads to band gap at zone boundaries. An analogous situation can be found in the case of photon propagation through a region of periodic refractive index. Similar to a semiconductor crystal, it is possible to develop artificial photonic crystals, which is nothing but a periodic arrangement of dielectric lattices resulting a periodic variation of dielectric constant or the refractive index. It is just like an electronic crystal where we have a periodic arrangement of atoms which results a periodic potential. While electronic crystals are mostly having natural occurrence, photonic crystals are mostly engineered structures. We will have a detailed discussion on photonic crystals in module 5. The concept of Brillouin zone is valid in the case of photonic crystals as well. In the case of photonic crystal, the same Bragg scattering produces diffraction of optical waves. So we have an identical expressions for Bragg's diffraction condition. Minor modification is the inclusion of the refractive index of the medium. It is actually the effective refractive index of these two materials, or the average refractive index of the two materials. Since the lattice spacing need to be of the order of the wavelength of the propagating wave, this equation suggests that the lattice spacing of the photonic crystals can be much larger than that of an electronic crystal, as the wavelength of photons are much larger than electron wavelength. So the length scale of the periodicity is quite different in photonic and electronic crystals. If we consider a photon of wavelength approximately 500 nanometer, It requires a lattice spacing of around 200 nanometer for the photonic crystal, assuming the normal propagation and an effective refractive index of 1.25. Now you see the difference of the spacing required. It is orders of magnitude higher than the spacing requirements compared to the electronic crystals. Similar to the band gap splitting in electronic crystal, periodic variation of dielectric constant gives band splitting in photonic crystal as well. There exists a forbidden frequency region between the two allowed bands, which is called the photonic band gap. Similar to electronic band gap, no photon frequencies in the gap region of the photonic crystal corresponds to the allowed state for this medium. Hence, the photons in this frequency range cannot propagate through the photonic crystal. Physically, what happens is that these photons of band gap frequency meets the Bragg's diffraction condition, and hence the photons of these frequencies are multiply scattered by the scattering potential produced by the large refractive index contrast between N1 and N2, resulting in their localization. Localization means that there is no wave propagation through the crystal. In other words, if photons of frequencies corresponding to the band gap region are incident on the photonic crystal, they will be reflected from the surface of the crystal and will not enter the crystal. If a photon in the band gap region is generated inside the crystal by emission process, it will not exit the crystal because of its localization. There are many examples that could be found around us which manifest this selective reflection from photonic crystals. These are some of the examples found in nature along with their scanning electron microscopic images. You can see that the selective reflection from butterfly wings or peacock feathers are actually due to this kind of photonic crystal effect due to the periodic arrangement of the structures of different refractive indices.